In the previous video, we introduced the topic of synchronized measurement technologies, or SMT, and why they are useful in power systems. In this video, we will discuss the overarching concept of wide area monitoring, protection and control, also known as WAMPAC. We will also learn what role SMT plays here and which functions we can implement with it. As we discussed in a previous video, synchronized measurement technology enables wide area monitoring. But why is this technology so important? This diagram shows the timescales for different control actions. As you can see, in the event of a fault, the protection and control devices in the substation should engage. Typically, this primary protection will operate within 100 milliseconds, maybe faster. It's very fast. If the primary protection does not operate properly, then the operator will need to act. And an operator neither can nor should respond to every spike or every variation in the incoming data, because these signals might be false alarms or just a glitch in the data. This means the operator must wait until multiple signals come in, showing that the primary protection indeed has failed. And this may take up to 1 minute. Deciding on and performing the necessary control actions may take even longer. Therefore, we have a certain control gap between the fast 100 milliseconds range and the manual minute range. Wide area monitoring allows us to bridge that gap by using algorithms to detect problems and using data from PMU data streams. We can then use automated wide area control to take corrective action based on data. This means that if primary protection fails, we have a relatively fast backup action. So who benefits from such a wide area monitoring system? From the perspective of the system operator, it's easier to prevent failure. And if still something happens, it will be quicker to restore the system. From the perspective of the generators, having fewer outages means that they are able to have higher generation availability, selling more energy and making more money. From the perspective of the transmission and the distribution, the system can be monitored in real time. This reduces the risk and the impact of disturbances. Let's take a look at the usage of WAMPAC in terms of time. In the long term, it's possible to use measurements from PMU devices to improve the dynamic performance of the system. For instance, it's possible to use data for tuning machine governors or power system stabilizers. It's also possible to take short-term actions, even before an event. There might be certain signals and measurements indicating that the system is getting unstable and some event is likely to occur. We can then take preemptive control actions to reduce the chance of a blackout. One such emergency protective scheme is called islanding. This involves deliberately separating the power system into smaller, self-sustainable islands to keep them stable. Finally, there are post-event actions in which the system is analyzed and repaired after an incident. For example, it may be necessary to resynchronize separate islands, island networks, before connecting them again. Currently, each transmission system operator and distribution system operator has its own control center, managing the power grid only within their designated region. This is simple to implement, but it means if there are oscillations or instabilities due to the interaction between multiple regions, it can be difficult to detect and prevent. So in future, we might want to have something like a centralized, large-scale super operator who can use wide area monitoring to combine measurements from many regions. This would allow for improved control of electricity networks, but it would create also a single point of failure for the entire network. In order to avoid that single point of failure, it might be preferable to establish a decentralized, large-scale grid operator network. This means that multiple super operators would collect measurement data from several transmission system operators while also synchronizing their actions. Although this system would be more secure than a single operator, it is of course more complex to implement and might also lead to higher costs. One application of VAMS is generator coherency identification, which is the exercise of finding out which generators in a system oscillate together. Here you see the post-event frequency response of 10 generators. The black and the red generators are independent, while the green ones form a group and the blue ones seem to form another group. They oscillate together. Looking at the one-line diagram of this system, we can see the groups of generators. These groups are important to know if you want to perform a system split. Wide area measurement based on PMUs enables such advanced applications. To summarize, in this video, we have discussed wide area monitoring, protection and control systems. First, we learned about why these systems are so important, which gap they are filling, and how different stakeholders can benefit from the implementation of wide area monitoring. Then we covered various types of coordination and had a look at an example application. Thank you for watching.